hands. I can tell that we are gonna be friends.
Have you ever wondered how a light switch turns on the lights across the room?
It's because the light switch and the light bulbs are connected in a circuit. When dealing with circuits and electricity, there is not one, but two important laws we follow.
These are called Kirchhoff's laws.
Gustav Robert Kirchhoff was a physicist who lived during the 19th century.
He developed these rules which have significantly impacted our understandings of electricity and that allow us to do simple tasks such as charging your phone and heating up your food.
Quick sidetrack.
The relationship for Ohm's law is between voltage, current, and resistance. The equation we use for Ohm's law is V equals IR.
Ohm's law is only valid for a certain type of resistor, which are classified as ohm. But for our learning purposes, we assume that all resistors are ohmic. Thus follow Ohm's law.
Now, back to Kirchhoff.
Kirchhoff had two rules, the junction rule and the loop rule.
The junction rule says that all of the current going into a junction has to equal all of the current coming out of the junction.
This was proven true through conservation of charge. The loop rule said that the increase of voltage equals decrease of voltage, or that the sum of the change in voltage was zero.
This is true due to conservation of energy.
This is our good friend Bob. He kind of looks like an onion today, but he'll help us understand the junction rule.
Bob goes to school every day, just like you and me. We can think of Bob's classroom as a junction or a node. Every person that enters a classroom has to leave at some point. They can't just disappear into thin air.
Bob has 30 classmates. Even if these people don't all enter together and don't leave at the same time, we can see that by the end of the day, all 30 people have entered and exited.
Now, let's solve this problem by applying what we learned from Bob.
Each of Bob's classmates can be considered an amp of current. If 7 classmates enter the classroom and 3 exit this way, you know that 4 have to exit this way because 3 plus 4 equals 7.
The loop rule is also quite simple, so simple that we don't even need Bob's help. Sophie is about to walk around a closed loop, which means she will end up in the same place she started. The point of the loop rule is to add or subtract the voltage drop across each circuit element, such as a resistor or a battery. Every person Sylvie passes can be considered a resistor. Every staircase Sylvie passes can be considered a battery. The top of the staircase represents the positive terminal of the battery, and the bottom of the staircase represents the negative terminal of the battery. The change in elevation represents the change in voltage.
I will start walking here. Look, a friend is walking towards me. Now I can high-five him. This is a really positive addition to my day, if you know what I mean. Wink. Look, a person is walking the same direction as me, and they really want to talk. This is a really negative addition to my day, if you know what I mean. Wink! Hold up! Just to clarify, we're applying Ohm's law and the loop rule.
As mentioned before, Ohm's law is V equals IR.
In this scenario, we're disregarding any numerical values to current and resistance, and only looking at the direction of the current in the resistor relative to the direction of the loop.
This will help us figure out whether to add or subtract voltages.
Now we may resume. Look, stairs. I'm about to go up them, which means my elevation is going to rise. In terms of voltage, that means my voltage is also going to increase. Look at that! Stairs again. I'm obviously going to go from the top stairs to the bottom of the stairs. So in terms of battery, I'm going from the positive terminal to the negative terminal. My elevation is going to decrease, so my voltage is going to drop. Now I'm in the same spot I started in, and I have finished my closed loop.
So when Sylvie walked in a closed loop, she had one positive addition to her day and one negative addition to her day, making the change in elevation 0. Thus, the sum of change in voltage was 0.
Now we can solve a problem. Look at this loop. If we use the same analogy as before, these resistors are people and these batteries are stairs.
You can pick any directions for the direction for the loop. For this problem, we will make the direction of the loop clockwise, just like the direction Sylvie walked.
When we get to any resistor, we will multiply the given current and resistance, and for the voltage, we will just write down the given voltage. Keep in mind, problems usually ask us to solve for unknowns, so pull out your algebra skills.
Let's begin at this point. As we travel along, we get to this first resistor. The resistor is labeled as 15 ohms, and the current is already labeled as being 15 amps and is going to the left.
So by applying the analogy from my walk, the 15 ohm resistor is a friend walking in the same direction as me, thus giving a negative addition to my day. This means we will subtract the voltage along the resistor, which is 15 times 15 because V equals IR.
As we continue along the loop, we get to a battery. Our loop goes from the negative to the positive terminal, which is the same as climbing up the stairs and having an increase in elevation. Thus, we add the voltage of 5 volts.
Now we get to a second resistor. The current is going in the opposite direction, so we're going to add the voltage, seeing that now Sylvie can high-five a friend and is happy. However, I2 is unknown, so we're going to write it as I2 times 38.56 ohms.
By now, we should be used to the swing of things. We get to the second resistor. The current is in the same direction as the loop, so we subtract 15 times 9 ohms.
Finally, we get to an 8-volt battery, and it's also going from the negative to the positive terminal, so we add 8 volts.
Now we finished our closed loop, and we have this algebraic expression. The loop rule says this expression equals 0, thus forming an equation.
We can now solve for I2. At least now you know all the secrets of electricity and can basically do anything.
I mean, anything regarding analyzing loops.
Well, now that you know the basics, you can continue in your electricity travels and solve even more complex loops.
And now you can go tell all your friends how smart you are.
And now,
all of the bells from this video. Yay!
Google said that.
Back to school, ring the bell.
Huh?
Literally made the weirdest
I'm so I can tell that we are gonna be friends. Walk with me, Susie, through the park and by the tree. We will rest upon the ground and look at all the bugs we found. Safely walk to school without a sound. Safely walk to school without a sound.
Wow, that was I went back against the Hold up!
We clean up and now it's time to learn.
Hold up!
In this it's time
we're applying
As mentioned before, O's law is B.
Nouns and books and show and tell. Playtime we will
I'm just not going into
class.
Yeah.
Teacher marks our head against the wall. Teacher marks our head against
This is wrong.
the wall. We don't notice anytime. We don't notice
Oh God, only valid. Certain types of resistance.
Sorry.
I just go out and lay
Teacher
down.
thinks that I
If I can see your eyes, I'm like,
She
wow.
likes the way you sing. Tonight I'm in bed. Silly thoughts go through my head.
He's walking.
Oh, dude. When I wake tomorrow, you and I will walk together again.